So the next, so the next speaker is Filippo. Filippo Cremonese is a security researcher. Is specialized in is specialized in web security, cryptography, and as we can see, also reverse engineering and binary analysis and basically exploiting. During the day, he's working at a Rev.ng. He plays. Can you put the slide, please, Marzio? During the day, he plays with a binary analysis tool they develop at Rev.ng, and at night, and so during his spare time, he plays CTFs with Tower of Hanoi. So, and also Macaroni and other teams. So he's working on his master thesis at Politecnico di Milano, and aiming to discover vulnerabilities in X509 parsers. So the topic it will talk us about is very hardcore. It's about binary editing and with high level languages. So basically, he will show us how he implemented a tool to patch an executable without having to rewrite tedious assembly and doing complex binary manipulation. He did so by abusing the LLVM just-in-time engine, and the tool that is Crispr allows you to statically rewrite individual function in an existing binary using C or any other language, but he will explain why he used C. And possible to call existing functions or non-existing function externally, and also how to patch, how to tackle some challenges like having to patch binaries that ends up in a patched form bigger than they were initially. So it will also explain and show us some example with ELF, and explains also some peculiarities of ELF format and how these techniques applies to ELF. And so this tool is potentially a game changer in real world binary patching scenario, or almost real world, like a CTFs, especially attack and defense CTFs, and it will be released as open source. So let's move on to the next talk. And so Filippo Cremonese, so you will take the stage.
Hi everyone, and welcome to my talk about static binary patching using high-level languages. Now, a couple of words about myself. My name is Filippo Cremonese and I work for Rev.ng. We are a small company and we do all things binary, so ranging from binary analysis to writing emulators and compilers. We do a lot of interesting stuff. For instance, we are the maintainers of the hexagon support in QEMU. We also developed an architecture-independent static binary translator, and we are in the process of developing a new decompiler which we call Rev.ng, for which we recently opened access for our nightly builds. So if you're interested in that, please check out our website and register to gain access. Now, when we talk about binary patching, we mean altering a compiled program behavior without recompiling it, also because we may not have access to its source code. Now, there are a wide range of reasons why you may want to do it, and one of those is you may want to fix a bug or vulnerability that you find in a binary, or maybe you want to add some dynamic analysis features to it, so maybe trace function calls and function parameters, or add some code that collects some statistics, for instance. Patching a binary is also useful if you want to implement some cheats in a game, or if you want to place a backdoor or bypass some pesky DRM. So I like to go by example, and I will use a quote real-world example taken from CTF 2018 Finals Ribbons Challenge. Now, this challenge had a function which is this, and it has a vulnerability in the memcopy usage. As you can see, you may already have spotted it. The memcopy uses as its length the string length of the new password. Now, the new password comes from the user, so the user is able to provide a password which is too long to fit into the password field of the channel structure. And you cannot see it from here, but this allowed you to overwrite a pointer, and by overwriting that pointer you could then leak memory, and with that primitive leak passwords for other channels and ultimately leak some flags. Now, the RusTF is an attack defense CTF, so during the game you're not only required to exploit vulnerabilities, but you're also required to patch yourself to defend against others. So the usual approach to this is to patch manually. So you have to go find the vulnerability and then write some assembly manually to patch the vulnerability out. Now, this specific instance is not even that hard to do. For instance, one way to do it is to change the call to string length into a correct move into EAX to have the correct size that gets then passed to memcopy. But this is just not nice. It's tedious to write assembly manually, and it's also really error prone, and when time is of the essence, such as during a CTF challenge, or when you just don't want to get something wrong, if you're a bank and you want to patch some program, this is just not a nice approach. So wouldn't it be nice instead if we to be able to decompile a function, edit it, and click apply without any hassle, any manual work? And this is what we're trying to build with Crispr. Now, Crispr is a tool that applies arbitrary patches to binaries, and it does so in the least invasive way possible. So if possible, it does it even in place, just as it would manually. And this means that there is no size increase and minimal modifications to the binary. But it also supports some advanced features, such as the ability to link new dynamic libraries together with your patch. It's also completely static, and by that we mean that we do not require any runtime, and there is so almost no performance overhead. There is no reliance on any operating system or on any debug features. We plan to integrate Crispr into Rev.ng UI, so you will be able to decompile a function, edit it, and click apply, literally. We also like to mention that we built it using LLVM because we use LLVM every day for our work, and we think that it's a really great framework suited for doing something like this. Now, this is the high-level overview of how Crispr works. We start from our original binary, and using the tool of our choice, we decompile it and we edit the source of the function that we want to patch. From this, we take the source code of our patch and we compile it using a custom compiler to an object file. Then we pass this object file and the symbols recovered from the original binary to a linker to produce some linked code. And then ultimately we pass it to a component which we call the patcher, which takes the original binary and the new code that we produced, and it merges them to produce a patch binary. Now, this process is quite involved, so I will start from a simple example, and let's assume we want just to patch the original function with a correct version which uses string copy instead of memcopy to copy the password from the user. Of course, using the correct size boundary, and ensuring that the last byte is zeroed. Now, to do this, the first thing we want to do is to translate our C source code to LLVM IR, because Crispr takes LLVM IR as an input and not any programming language source. Now, to do this, we just use clang with a couple of flags to instruct it to generate LLVM IR and to disable exception support, because we don't need it and it will generate more compact code. Now, Notice that because Crispr uses LLVM IR as an input, it is possible, at least in principle, to use any programming language for which there is an LLVM front-end. Now, not all programming languages are well suited for this task because many programming languages require a complex runtime, a big runtime to work. So it would mean that you need also to include the runtime for the language together with the patch, but you can write your patch basically in any language you want. Now, the next step is to compile the LLVM IR to actual machine code. And to do this, we abuse the LLVM ORC APIs to create a custom compiler. The LLVM ORC APIs are meant mainly to create just-in-time compilers, but they're really flexible and they allow you to create your own compiler by stacking layers. And so we have a first layer, which we call our isolate sections layer, which places each function in its own separate section, and this will be needed later at link stage, and we'll see in a moment. Then we do some optimizations to increase performance and to decrease the size of the code that we're going to generate. And then we have a compile layer which takes the IR and lowers it to actual machine code generating an object file. Then there is a linking layer which takes the object file generated by the compiler and it forwards it to the linker. We've chosen to use LLVM ORC APIs because we want to support cross-compilation, and LLVM ORC APIs allow you to support cross-compilation really easily. Also, they are in process. You can use LLVM as a library, so you don't need to call any external binaries, which is handy. And lastly, this is more of a personal reason, but it provided me an opportunity to learn how LLVM and JIT compilers work, so that's a nice plus. Okay, after we have our object file, we need to link it. And to link our object file, we need to tell our linker where the new functions that we are compiling will be loaded in memory at runtime and where the pre-existing functions can be located. And now we have a bit of a problem because what is the location that we can use for string copy that we're using? Because if you think about it, string copy is not a function proper of the program that you are trying to patch, but that is a function of the C standard library. And it turns out that there is an address that we can use for it in the program that we want to patch. And that is due to how dynamic library function calls work. So when a function wants to call a dynamic library function, what it does is it calls a stub in a special section which is called the procedure linkage table. Now this special section is generated by the linker at runtime together when the linker runs together with another section which is called the global offset table. Now these two sections are what's needed to call a dynamic library function. So the procedure linkage table contains stubs for each and every library function that's needed by the program that we're linking. So we'll find an entry in it that does the following. So the first instruction reads an offset inside the global offset table. Now this offset at the start of the program usually points to the instruction right next to the first instruction in the procedure linkage table entry. What this second instruction does is it pushes an identifier on the stack and then it jumps into the dynamic loader. The dynamic loader is a special program that is loaded together with our original program, and its job is to resolve to actually find the address of the library function that we want to call, so in this case string copy. It will also change the offset in the global offset table to point to the string copy function, and then it will jump to string copy. Now on subsequent calls, what will happen is that the procedure linkage table code will read the offset from the global offset table, and now this offset has been patched by the dynamic loader to point directly to string copy. So the execution flow of the program will go from our function to the procedure linkage table stub to directly the string copy bypassing the dynamic loader. So now that we know that where we can find all the offset that we need, we can invoke the linker with something like this. So we use section start to tell the linker where to place each and every function that we want to patch. And since we're trying to build an in-place patch, we tell that the section containing the change password function, the new change password function that we are compiling, will be at the same address of the change password function in the original binary that we want to patch. Then we have to define a couple of symbols for the functions that we used in our patch. So we have to tell the linker where save channel, the save channel function was, and where the string copy function is in the procedure linkage table. When we get the output from the linker, we can then just look up where the new function is in the code, for instance, using objdump or parsing the file, and we can basically just copy and paste the new code over the old one, and we are done. Of course, Crispr does this all for you automatically, and you do not have to invoke manually any command. Now, let's go back to our example and instead what if you wanted to try to apply a more complex patch, such as this? So you can see we call printf each time change password is invoked to trace the function invocations, and then we check if the new password that was supplied by the user is bigger than what should be allowed. And if so, we warn that an attack was detected, and we sleep just for 1 second just to annoy the attackers. And yeah, this might not be the best idea, but just stick with me for a moment. And then we implement change password correctly using string copy and ensuring that the last byte was 0, just as before. So there are a couple of issues with applying this kind of patch. And the first issue is that we are using sleep. So sleep turns out was not actually imported in the original binary. So there's no PLT stub for it. We have no address where we can jump to call sleep. And the second issue, maybe even bigger, is that if we try to compile our code and we check how big the function that we compiled is, we'll see that we will generate a function which is bigger than the original one. So the new code won't fit over the old one. We can just overwrite the existing function because we will also overwrite what comes after it. And it turns out it's not enough to just append the new function and the new data at the end of the file because of how binaries work. And so to solve these two issues, we need to know a bit more about what a binary file actually is. And from now on, we'll talk specifically about how ELF binaries are made, but many of these concepts will also apply to other binary formats as well. So what's an ELF anyway? So ELF is the file format for binaries as it's used in Linux, in BSD, and many other platforms. And ELF files always start with a header which has this format. Now, first of all, there is some magic identifier. If you've ever hex dumped a binary, a Linux binary, you might have noticed that it will always start with hex 7f and then ELF, as in ASCII ELF. Then there is a type identifier which tells you if the ELF you're looking at is an object file or if it is an executable file, for instance. There are many other fields in the ELF header. For instance, there is the entry point address, and that is the address where the program execution starts when the program is being run. And there is also a couple of offsets into the file which tell you where the program headers and the section headers are. And what are those? Now, an ELF file can provide two views of the same program. Now, the first view is provided by the sections in the section header table. Now, sections are used by the compiler and by the linker, and then what the compiler and the linker reason about. Section headers are not actually required for execution, and that's why when you run strip, it can safely strip out the section informations, and the program will run just fine. The second view is provided by program headers, and those are required for execution, and they're what the linker generates, and they're generated by the linker. Now, they are required. We can inspect the program headers of a binary using our trusty readelf utility, and there are many types of program headers, but those are the main ones that we need for this talk. Now, probably the most important program header type is the load program header. Now, load program headers are important because they describe the memory map, so they tell what the program needs to have in memory in order to run. Also note that this program has two program headers of type interp and dynamic, and you will find those two types of program headers in any dynamic program, that is, in any program that uses dynamic libraries. Now, the first header, the interp header, specifies what's called an interpreter, and it's also known as the dynamic linker. And the second one is information needed by the dynamic linker to do its job. Now, this is what happens when loading an ELF, dynamic ELF program. So on the kernel side, the kernel reads the ELF header and it finds the program headers from the offset written in the ELF header. Then, if there is an interp header, it loads the interpreter, which is just another program. Then what the kernel does is it sets up the memory map of the program by following what's written in the load program headers. It does a lot of other things, but the other thing that concerns us that the kernel does is it allocates the stack and it fills the argument vector, so that is the vector that contains the arguments passed by on the command line. And also it fills the auxiliary vector, and that's a little known vector of parameters that the kernel passes to programs that are being run. And one of those entries we care about because it contains the address of the program header, of the program headers. Then the kernel will jump into the dynamic loader. So the dynamic loader, remember, its job is to load dynamic libraries, and to do so it needs to find the content of the dynamic section. To do so, it finds the address of the program headers by reading the auxiliary vector, and from there it looks for the dynamic program header. Now, the dynamic program header points to the dynamic section, and in the dynamic section there are many types of entries, and so these are the main ones. So there are needed type of entries, and what those do is they specify the name of some required libraries. So for instance, our ribbons binary needed two libraries, and that would be the libc.so.6, so that is the C standard library, and also libmicro-httpd. Then there is the string table, because actually what the needed entry do is specify an offset inside a string table. So this table contains the names of required function and required library names. There is also a symbol table which describes which symbols, and that is basically which functions and which variables are referenced by the program being loaded. Then there is the rela entry type, and this points to a table describing basically which operations are needed by the linker, the dynamic linker needs to do to actually write the correct offset inside the global offset table that we've seen before. There is an entry also to get the address of the global offset table, and then there are a couple of entries needed by basically performance optimizations, which point to some hash tables which are needed to improve the symbol lookup speed. Last but not least, there's also some entries required to implement symbol versioning, and that's used for maintaining backwards compatibility in libraries that need to do it. So to be able to link new dynamic libraries or import new symbols inside our patch binary, we need to basically adjust and extend all of those informations. And this is what we do to implement an out-of-place patch. We basically patch, extend, and append at the end of the binary all of what we've previously said. So we get the new code, the new data, and the new read-only data that's needed by our patch, and we append it to the end of the binary. Then we take the original symbol and the original string tables, and we extend those, and we append those at the end. We also take the original relocations, and extend them with the new relocation that are needed to import the new symbols from the dynamic library that we're importing, and we place them at the end as well. Same thing goes for the dynamic headers, which we now need to fix to point to the new patch information. We also need to patch the symbol versioning information and to create new program headers and section headers which map and point to the new data that we have patched. So the last two things that we need to do then is to patch the elf header to point to the new program and section headers. And lastly, we have to detour the original function to point to the new code. So basically we insert a jump at the start of our original function, so in this case save channel, to jump into the new version of save channel. Now, I've talked enough and I think it's time for a demo. So here we have the original binary, which is called ribbons, of course, and we can run this binary. And what I have on the other terminal is an exploit for it. So if we run this exploit, what it will do, it will add a number of channels to the service. Then it will use the vulnerability that we have described earlier to leak passwords for those channels. So as you can see, it has found many passwords for the channel that is for the channels that it has just added. Now, we have a patch ready for it, which looks like this. It's basically what I've shown earlier. So what we do is we call printf each time the change password function is invoked, and we also check for the new password size. If it exceeds what's the maximum allowed, it warns us that an attack was detected, it sleeps, and it does nothing. Otherwise, we have the correct implementation of the function just as before. So we already have compiled the patch to LLVM IR, and it's here. Oops. And so this is basically a high-level assembly. It's not really that interesting to read it because it's compiler generated, so we won't even be necessary to touch it. And what we can do now is to apply the patch by calling Crispr, and I have a script ready just because the demo gods are never kind. So I will just call this script, which will call Crispr, and notice that I am passing an argument that tells it to link the standard library again, because we are now using sleep, which was not imported by the original binary, and the patch LLVM IR file. So I can now apply the patch, and this will have generated a patch binary called ribbons.patched, which we can then run. And now I can run the exploit again, and the exploit will add the channels, but then it will try to exploit the program failing because the password change was refused. Now, as we can see, the patch program printed that change password was called and also that an attack was detected. So our code is being executed. Now, I want to end by being forthcoming about some limitations that we currently have. So the first one is that we cannot call the original function because we are altering it, either by overwriting it in case of in case of an in-place patch, or because we are detouring it by placing a jump at the start. So for us, this is not really a big issue because our aim is to be able to decompile, edit, and replace the function, so the functionality will be preserved, and if you need to, for some reason, invoke the original version of the function, you can just include that together with the patch and call that instead. We also currently only support x86, 64, and binaries. This is not an inherent limitation. We just need more time and engineering effort to support other architectures and other binary formats. We do not support self-modifying code or integrity checks, but that's pretty natural and to be expected. And a bigger problem that we have is for inline functions, because when a function gets inlined, you lose the function boundary that you have normally when calling a function which was not inlined. So being able to replace that function basically means to patch the whole function where the function that you want to patch was inlined into. We also have a lot of optimizations that we can implement to basically optimize the size of the binary that we produce in case of an outline patch. But this is because we want to prioritize creating a general solution before optimizing. So what we have implemented here should work basically for any binary, and it's really general. So that was it. Thanks for your attention, and I will now be available for a live Q&A session.
Well, we are back. So thank you, Filippo. That was something really amazing. So this is some field I'm not really skilled on, but it sounded like some actual game changer. This tool you developed, right? So let's go with the questions. First of all, we had a question that our moderator deleted, but I wanted to share with you. It wasn't a question; it was just a message from some of your groupies. So it went like, "Efcremo, you are handsome, macaroni groupie." so you have some fans over there. Apart from that, so let's move to the first question. So the first question is, can you better clarify what do you mean when you say that with this approach, LLVM IR approach, allows you to work in process and no need to call external binaries? And how does it compare to other known approaches? If you can name any. Okay.
Yeah, so it's not the LLVM using LLVM IR per se that allows us to work in process, and it's mostly using ORC. As of now, the tool is not fully capable to do in process because the patcher is still written in Python, and because we are actually invoking an external linker. But our goal is to, since our goal is to integrate this tool inside Rev.ng, it would be nice to have something that we can have fully in process and does not require to call external binaries or external scripts. So I guess that answers the first question. The second, how does it compare to other known approaches? I don't know if you mean other approaches as in using LLVM IR versus not using LLVM IR.
Probably yes.
I don't know of other tools that use LLVM IR, but that's not the focus on patching, because the LLVM IR is the. I mean, what's nice about using LLVM as a toolchain is that we can, at least in principle, use any language as a starting point for writing the patch, with the caveats that I explained earlier, that not all languages then are really suited for this because of their big runtime. For instance.
I don't think you're going to patch in Java something written in C, no?
yeah, you probably don't want to do that. But it would be interesting and at least possible in principle to use, for instance, Objective-C, for which I am quite sure there exists an LLVM front end, to patch an Objective-C, a program that was written in Objective-C. So to use the same language that was used for writing the original binary. Now, that might be a challenge. For instance, for C++, there is the exceptions. There are a lot of things that are hard to handle. But our goal is definitely to support some of these scenarios. if the other interpretation of the second question was how does it compare to other known approaches, as in other tools that allow you to do this, I'm not really aware of any tool that allows you to do this even in place. I'm not aware of any open source widely used tool that allows to patch binaries in place, but that's kind of that thing that you do manually by assembling something and putting it in place. The cool thing that we've done, and not that I have invented any of this, because there are many at least answers on Stack Overflow where someone described the general idea on how you can do this, but calling external libraries new functions, that's the real pain to get it working. That's what I've spent most of the time getting it working. So I'm not aware of any tool that allows you to do that. Never seen any of it.
Okay, thank you. Another question is, did you use the tool to do massive patching during CTFs? So probably it refers to the fact that you are a CTF fan. And did you find and then if yes, tell us something about that. And then any other real world scenario where you successfully used it? So you mentioned some of them, like patching of binaries, so for vulnerability remediation or mitigation, and backdooring other binaries or DRM. So if I can recall.
No, no, I mean, not yet, at least. So okay. Not satisfying answer, but.
Okay, and what about the first question related to CTFs?
Yeah, no, I mean, I did not use the tool in a real world scenario yet, because it has been, I actually promised my teammates that the tool would have been ready a lot of time ago, but you know how those things go. So no, not yet. I'm quite convinced that this tool can be used in CTF scenarios and also in real world scenarios to patch up binaries, though.
Okay, cool. Third and last question. So from Andrea, ciao Filippo, nice work, thanks. I was wondering if you tested the tool by verifying that the functionality of the patched program is preserved. Did you find any case where the patching broke the program? I think so.
So there are definitely programs that will break when using this tool, but we have not done extensive testing yet. The approach, as I said, is pretty general, and there are not that many things that a binary can do, that at least the legit binary can do to such that our approach does not work. I mean, one is to have a function so small that even the jump at the beginning of the function to jump to the patch code is if the function is too small, we cannot do even that. But I'm not sure you can even generate a function so small with a compiler without using inline assembly or something like that. And the second approach is some architectures actually inline data inside the code. That's still a problem for now. If for some reason the program goes to read that data back and we overwritten it, and then that's a problem. Yes, and we have not managed to do it, and I anticipate that would break our method.
Okay, thank you very much. So I don't see any other question right now. As usual, as I told for the previous talk, I encourage the audience to write to the Slido chat you find in the nohat.it/live. There is a room dedicated for each talk, and this is F Cremonese. So you can continue to write on that, and Filippo will be updated on that and provide you answer. So thank you very much, Filippo, for your interest and for providing such a valuable work here, and for presenting it at NoHat.
Thank you. Enjoy the rest of the conference for the audience.
Thank you.